Hello again. This is Karl Rittger representing Cold World Consulting, and along with ICIMOD SERVIR-HKH Himalaya Initiative and NASA SERVIR, I'd like to welcome you for the fourth and last lecture in a series of 4 lectures that accompany our hands-on training each Monday and Wednesday morning. In the 3 previous lectures that Rajesh shared, which hopefully you've all viewed by now, I talked about snow hydrology, the remote sensing of snow extent with visible and near infrared wavelengths, the remote sensing of snow volume with passive microwave wavelengths, the energy balance and reconstruction of snow water equivalent at both the point and over mountain ranges and basins. We consider reconstruction of SWE more accurate than many of the passive microwave and other coarser scale modeling efforts. Today, we'll talk about the basics of machine learning and using machine learning to fuse snow cover and albedo data from MODIS and Landsat. We'll also talk about the use of our SWE reconstructions to estimate SWE in real time using machine learning techniques. Next, we'll talk about data from a NASA project our team works on to produce SWE and melt from snow and ice called HiMAT-2. Finally, I'll show you a set of operational data over the Western United States that we'll hope to extend to the Hindu-Kush Himalaya region in the next year, and existing assessments of SWE in the Hindu-Kush Himalaya. Here's a bit more detail on the topics covered today. We use machine learning because of issues with other data. For example, passive microwave SWE begins to saturate at 150 millimeters. It's useful for context when we compare to previous years, but the total volumes are much less than the actual amount of snow. Modeling at the global scale, like ERA 5, which you worked with in the first lab, has a longer time series and no saturation issue, but is a coarse resolution as well. Reconstruction is the most accurate, but is only retrospective. We'll discuss machine learning over Afghanistan that builds on the reconstruction. Next, we'll discuss a technique that we are using to combine the strengths of multiple satellites. MODIS provides daily estimates of snow surface properties at 500 meter scale, while Landsat provides the same properties at a 16-day intervals with much higher spatial resolution. We use machine learning to combine the temporal frequency of MODIS with the spatial resolution of Landsat. After that, I'll talk a bit about current research we are doing in a NASA project. In the project, we're estimating SWE over all of the region. In addition, we're separating components out so that we know how much water comes from snow and how much comes from ice. Finally, I'll show the operational data visualization of seasonal snow from both the National Snow and Ice Data Center and the US Air Force Weather Squadron. In machine learning, there are 2 main types. There is supervised learning and unsupervised learning. In unsupervised learning, we're using a set of known features or predictors that we can easily measure and are readily available. We use these features to look at associated responses, usually something we are trying to predict. For example, snow cover, snow albedo, or snow water equivalent. We use a machine learning model that is trained on a set of both features and responses. Once we train the model, we use it to predict the response at locations or times where we don't know the response. There are also unsupervised learning techniques which do not have a model response, but are used to identify structure and patterns in the data. Supervised learning is basically used for 2 things, classification and regression. For classification, logistic and probit regression are used, as well as support vector machines, decision trees, and discriminant analysis. The goal is to put everything in a class. Is it this or is it that? Regression methods use linear regression, decision trees, neural networks, and Bayesian networks. I'll return to decision trees shortly as we use these. Unsupervised learning, in contrast, uses principal component analysis, empirical orthogonal functions, and neural networks. Returning to decision trees for supervised learning, for both classification and for regression, a single tree is shown, as shown in the last slide, tends to overfit the training data, and then when used to predict on a different set of data, doesn't work that well. An ensemble or groups of decision trees can be used to create a bunch of separate decision trees that are fit on subsets of data. When the prediction is done, this type of approach uses the mean of individual sets of trees to do the prediction. This approach works significantly better than individual trees for predictions. An approach called the random forest is used in both machine learning for SWE and the Landsat MODIS fusion I'll talk about more today. For random forest, an ensemble is used, and at each node, break, or decision in the tree features, also known as the predictors, are randomly selected. The effect is that the trees are not that similar to each other, and the predictions tend to be better. So that you have a better idea, here's a simple example for downscaling daily MODIS to 30 meters like Landsat. On the right is a fit for a single decision tree. In this decision tree, MOD stands for MODIS, X and Y are for location, and ELEV is for elevation. On the left side of the tree, there's a split based on MODIS at 36.5% snow cover, giving two different predictions. On the right side is a split depending on the Y coordinate or latitude. For the right side, further splits are made on the same predictor or other predictors. This is a single tree. For ensemble methods, sets of trees like this are used. For the example of a random forest, the ensemble of trees chooses splits at random. I'll now show you three examples that include a single decision tree, an ensemble, and a random forest that we use. This example is for a single decision tree. On the left, we have MODIS data at 500 meter scale, and in the center, Landsat at 30 meters. For a single decision tree, we get the predicted values on the right. It is clear that this method doesn't work very well. It looks even worse than the MODIS data on the left. This is an example for an ensemble of decision trees. As in the last slide, on the left, we have MODIS data at 500 meter scale, and in the center, Landsat data at 30 meters. On the right side, you can see that the ensemble does much better than a single decision tree. Some of the high resolution is visible in various regions. It's a step in the right direction. The splits on predictor variables are driven by what every predictor variable is when it's the best predictor. Finally, we have a random forest. Again, as with the last two slides, on the left, we have MODIS data at 500 meter scale, and in the center, Landsat data at 30 meters. On the right side, we have the prediction from the random forest. You can see that the random forest does the best job at disaggregating or downscaling the MODIS data. We use this method in a project we are working on with the state of California to better understand the Sierra Nevada bighorn sheep, an endangered species. Our work focuses on the historical range of bighorn sheep, which has shrunk considerably over time. On the bottom is a list of predictor variables used in addition to snow cover from MODIS. This includes day of year, elevation, latitude, longitude, and some information about the mountain range, such as distance from the ocean, or which side of the crest the location is at, the windward or leeward side. The target variable was snow cover at 30 meters from Landsat. The bar graph on the upper right shows how important each predictor variable was. Not surprisingly, the snow cover fraction for MODIS at 500 meters was by far the most important. Here is a set of the results from two different dates, January 25th in 2006 and March 17th in 2007. 2006 was a very wet year and 2007 was a very dry year. On the left side is the MODIS data at 500 meters. You can see along the edges there are mixed pixels in the blue color. On the right side are 30-meter Landsat scenes. In the center are the results from the random forest model that we trained on 170 Landsat images. The effect of the downscaling that is evident on both dates is the clear sharpening of the edges and gradient of FSCA between the areas of snow and no snow. This is visible in the middle figures near the snow line where the snow transitioned quickly from a high percent to 0. The coarser resolution MODIS snow cover on the left tends to smear or smooth out these predictions or gradients, while the modeled snow cover in the center produces a more detailed spatial distribution like that of Landsat on the right. In this figure, I zoom in further so we can see more detail. There is also an additional false color image on the left. Snow looks light green and soils look red. In the second column is the Landsat data. On the top row, in the second column, you can see deep shadowing from the sun being low in the sky displayed as black. The third column shows the MODIS data at 500 meters. The right side shows the machine learning snow cover from the random forest model. As we saw on the last slide, there's an improvement near the snow line in the model on the right. On the upper right, we also see that there is no issue of the deep shadowing we saw from the Landsat observation in the second column. We are now working on a NASA interdisciplinary science project to project snow into the future to better understand how the bighorn sheep's habitat will be affected given the current projections for climate change. For hydrologic applications, we sum the snow cover from both MODIS and the machine learning random forest model and see that in combining the data, we maintained a similar total area from the original MODIS data. Here are the black lines and the red lines. For hydrologic applications, we are also working on fusing grain size now. The top row here shows MODIS snow cover and Landsat snow cover. The bottom row shows grain size with MODIS on the left and Landsat on the right. At the snow line, which is indicated by the red arrows, when the snow fraction is low, we have some biased grain sizes on the lower left. You can see that on the right, the grain sizes in many places from Landsat along the snow line are larger, which is what we would expect as the snow could be melting. We've started work on fusing this data in the Hindu Kush Himalaya. These two graphs show the predictor importance from the training model. On the left side is the predictor importance for snow cover. Similar to the Sierra Nevada in California, the MODIS snow fraction is the most important predictor. On the right side is the predictor importance for grain sizes. Here, the most important predictor is the local illumination angle that combines the slope and aspect of the terrain with the position of the sun in the sky, known as the solar zenith and azimuth. As we have learned with snowmelt, the sun is a big driver. Here for snow metamorphism, which makes the grains grow and lowers the snow albedo. It's the most useful variable in getting down to the 30-meter scale, as within each MODIS pixel of 500 meters, there can be terrain facing north that is shaded and terrain facing south that is always in the sun. This figure shows the analysis in the Premier mountain range. On the left side is the snow cover, and on the right side is the grain size. The first column in each set is the Landsat image, the second is the random forest model, and the third is from MODIS. The top row shows the full Landsat scene, and the second and third rows show two different zooms. As with previous examples I showed for snow cover, the middle column more closely matches the 30-meter Landsat on the right side. For grain size, that is also true for these figures. We use only 5% of the data from Landsat to train the model, so we have 95% of the data to look at how accurate we are. Most people call this withholding because they really withhold some of the training data. We find that we don't really need all of the data to train the model. We tested two models, one that allowed a continuous snow fraction from 0 to 100%, and one that had three classes from 0, 1 to 99, and 100%. The results from the continuous model are in pink, and the results from the model with three classes, in which we also use the random forest model, are in blue. With the three-class model, the bias in grain sizes are 10 micrometers, which is the smallest increment in our original model, meaning the random forest is doing really well at predicting at the 30-meter scale. Now that I've introduced machine learning, random forests, and shown an example of both snow cover and snow grain sizes which drive albedo, I'm going to show a study that we did using machine learning for real-time estimates of snow water equivalent, or SWE, in Afghanistan. This image shows the true color image of Afghanistan with an average of our reconstructed SWE from 2003 to 2011 on top, overlaid. The red box shows a MODIS tile that we did the analysis on that interestingly fits the country of Afghanistan perfectly. In the past lectures and labs, we've talked at length about the energy balance and reconstruction. Here on the left side, we have reconstructed SWE for 2003 to 2011 from April until July. You can see that 2009 was the wettest year with the most SWE, over 35 cubic kilometers of water. 2011, 2008, and 2004 were pretty dry years with less than 20 cubic kilometers of water. The graph on the right side shows the difference from average over the same period as a percent for each of the years. These estimates are used as predictors in our machine learning to predict real-time SWE. Remember, the reconstruction is only retrospective, while the machine learning allows us to predict snow water equivalent in real time. In addition to SWE from the reconstruction, similar to snow cover, we use a large set of variables for predictors in the training, including day of year, elevation, latitude, longitude, the elevation differences of the pixel relative to the highest pixel in each direction, distance to the ocean, and the southness of the pixel. These are all static variables and do not change from day to day. In addition to the reconstructed SWE as a dynamic variable, we also use the fractional snow cover area as a predictor. We also use the brightness temperatures from passive microwave. Recall from the first lecture that some of the passive microwave frequencies scatter more than others, so the differences between the two sets of bands are used. We were fortunate enough to have validation data or in situ data from the Aga Khan Agency for the Habitat. The map on the right shows the locations of the in situ observations, as well as the maximum snow depth. On the left side is a summary of what the snow climate is for the 81 stations on the map. Most of the sites were in alpine, some were in maritime, and some were in prairie, with the rest missing. We didn't have measures of density of the snow, and remember that SWE is the depth times the density. So using these snow classes, we assume densities that are typical for these climates so that we could estimate SWE from the in situ observations of snow depth. This graph shows a comparison of the modeled and measured SWE. On the x-axis is the SWE measured from the Aga Khan network, and on the y-axis is the SWE modeled from machine learning. The three graphs show the 1st of March, the 15th of March, and April 1st. The dotted line is the one-to-one line, and points that fall on it are well modeled and match the observations. You can see that the most points fall on the line, showing we were able to accurately predict the SWE in real time. This set of graphs shows a subset of the stations, and in contrast to the last graph, shows the SWE for dates from March 1st through the end of melt. The blue line shows the measured data from the Aga Khan network, and the red line shows the modeled data from machine learning. They match very well for wet sites, like in the top left, and for dry sites in the middle row, as well as moderate sites in other parts of this figure. We also looked into how related our predictors were. Here, yellow indicates there is high correlation. The yellow diagonal is when one variable is compared to itself. Some of the variables, like latitude and longitude, were correlated with distance to barrier and ocean. Fractional snow cover was also correlated with reconstructed SWE because we used the fractional snow cover in the reconstruction model. Generally, you don't want correlated variables because it makes it harder to understand which ones are the important predictors. However, correlation between predictor variables does not affect the accuracy of the model. The predictor importance graph on the right shows that the fractional snow cover was the most important predictor, followed by reconstructed SWE, elevation, and longitude. The brightness temperatures from passive microwave differences at 18 gigahertz and 36 gigahertz, the most used for SWE and passive microwave retrievals, came in next. This is perhaps some indication of the accuracy of passive microwave SWE, as it's the 5th predictor for estimating snow water equivalent in our machine learning model. Using the reconstruction as truth, as we know it accurately estimates SWE, we estimated the bias and root mean squared error by year in the top graph. Mean bias was about 14%, with errors ranging from 46 to 48 millimeters. In 2004 and 2011, you recall, were dry and wet years, and were particularly dry and wet at the beginning of the year. The bottom graph shows residuals, subtracting the reconstructed SWE from the machine learning prediction, and many of the errors fall around 0. We also analyzed the SWE by basin, again showing the bias on the top graph in blue is nearly 0 for all of the basins, with root mean squared error, RMSE, ranging from 9 millimeters to 45 millimeters. Looking at the residuals in the lower plot, the upper Kabul had the largest errors. The upper Kabul has much more SWE than the other basins analyzed. Now that we've reviewed machine learning methods and shown examples for snow cover, snow grain size which drives snow albedo, and SWE, we are going to show some data that we'll be generating in the next year as part of the NASA project called HiMAT-2. Many of these products will be familiar from our previous lectures, and there is one set of new products we'll introduce. First, we will be creating daily snow cover and snow albedo from MODIS from March 2000 to present. We will also be splitting the snow and ice cover into 4 classes. At the top of the mountain is snow that is on top of a glacier, snow on ice, or we call it SOI. We will also produce snow on land, or SOL. For glaciers, we'll produce exposed glacier ice, or EGI, and debris covered glacier ice, or DGI. As I mentioned, these will be daily at 500 meters. We'll use these observations from satellites to drive the reconstruction model to estimate SWE, as well as understanding the daily melt and snow sublimation. From the SWE, we'll use the SOI, SOL, EGI, and DGI classes to estimate the proportion of melt from each of these surfaces. During that process, we'll also produce annual maps of glaciers and analyze changes in the glaciers over time. I've shown figures before of snow cover and albedo, but here is a video of snow cover and albedo for a year. The video starts on October 1st, where there is snow at the minimum, and the albedo is on the lower side, as it has been melting all summer. As we move into December and January, snow will accumulate, increasing area. Snow albedo will increase as the new snow covers the landscape. The maximum snow cover will occur in February, and then snow will begin retracting in elevation while snow accumulates at the highest elevations, keeping the albedo high. As we move through the melt season towards June, snow will begin to decrease rapidly, and snow albedo will decrease as well. As we move towards the end of the summer, snow will again reach a minimum near October. We use the time series I just showed you for snow cover to track every pixel's minimum snow cover and ice throughout the year. This map shows the minimum snow and ice cover for a single year and subbasins of the upper Indus River Basin. We have done some analysis of a shorter time series of data in a previous project from 2001 to 2014 for 5 major river basins. We found that in the Sirdarya and Amudarya, snow and ice at the minimum is being lost, but we did not see a significant trend. The Indus Basin had a slight increase, but was also not significant. In the Ganges and Brahmaputra, we saw significant decreases in annual minimum snow and ice from 1 to 3% per year. We have done some similar analysis on a earlier, as I mentioned, separating the surface into different classes. The top row of the image here shows a false color RGB where snow and ice are light blue and soil and rock are red. The bottom row shows the class of exposed glacier ice, here in dark blue, snow on ice in light blue, snow on land in green, and debris-covered glacier ice in brown. Moving from left to right, you see snow on land decreasing, while exposed glacier ice increases and snow on ice decreases. This example is from my colleague Adina Rakovitnu using Landsat data. She published this work in 2019. We use this high resolution data from Landsat every 16 days to calibrate a model to do the same analysis at a 500 meter scale each day, which I'll describe next. This graph shows the spectral reflectance of both snow and ice. The snow is plotted in blue and the ice in red. The spectral and broadband reflectance are lower for the glacier ice, even though the snow is dirty. The result from ModScag is that we see a higher grain size for ice than snow. I'm sorry, that's a higher grain size for snow than ice. Let me rephrase. There's a larger grain size retrieved from ModScag for glacier ice than for snow. We used this information along with the permanent snow and ice maps I showed a few slides ago, in combination with the Landsat map classes from Medina to separate classes using daily MODIS data. To discriminate the various surfaces, we use this table. First, we know that everything with a snow cover fraction of 0 is either soil, rock, or vegetation. If the snow cover fraction is greater than 0, but at some point during the year, the annual snow and ice minimum went to 0, we know it's snow on land. If the snow cover fraction is greater than 0 and it has a small grain size, we know it's snow on ice. If the snow cover fraction is larger than 0 and there are large grains, we know that the surface is exposed glacier ice. We use the Landsat maps of these classes to set a grain size threshold to differentiate snow from ice. Currently, we are using a static set of glacier polygons from the Randolph Glacier Inventory, also known as RGI, to define the debris-covered glacier ice. So, with that method, we are able to separate the snow surface. We use our knowledge of that surface for each pixel combined with the reconstructed snow water equivalent shown here. This image shows our 2014 estimate for snow water equivalent. We ran our energy balance model at an hourly time step with daily outputs to estimate melt in the 8 subbasins of the Indus River, of the upper Indus River. The plots are sorted by total stream flow, with the upper reaches on the top left and the lower reaches on the bottom right. With the energy balance model, we can accurately estimate the stream flow volumes. Combining our surface partitioning with the energy balance estimates of melt, we can figure out how much of each subbasin's contributions come from snow on land, snow on ice, and exposed glacier ice. We haven't yet combined our debris cover glacier melt into this graph, but rainfall is from a separate product. At Besham, for the upper Indus, we show the mean annual proportions of melt from snow on land, snow on ice, and exposed glacier ice. As we expect, the largest proportions of glacier melt and snow melt over glaciers is in the highest northern glaciated basins. Though the Gilgit is adjacent to these basins, it has a much larger proportion of melt from snow on land or seasonal snow. While the Tarbella and Drasnala are in the south and not nearly as glaciated, they produce larger volumes of melt from seasonal snow. The Karmung to the east has the lowest flow, even with its large size, because it is a more arid environment where precipitation rates are lower. For example, the largest contributions from glaciers are in the Shyok, the Hunza, and the Shigar, with 35, 41, and 51% respectively coming from exposed glacier ice. The largest contributions from snow are in the Gilgit, the Astor, and the Drasnala, with 67, 77, and 81% coming from snow. Here are two example subbasins not in the Indus, the Vaksh and the Narin. The graphs on the left show the melt volumes on a monthly basis, and on the right side show the melt volumes on an annual basis. You can see in the monthly graphs that the snow melt is happening from March to August or September. In May, some glacier ice starts to be uncovered and melt, and then that volume grows over the summer as more snow melts away. On the graph on the right side that shows the annual estimates from 2001 to 2014, you can see that the total melt volumes and proportions change from year to year. Over the next 2.5 years, we expect, using this type of approach and analysis, we will better understand the contribution of snow, glaciers, and rainfall to stream flow through our NASA project. I'll now show parts of these data streams that we're doing in real time over the Western US. We've also implemented most of what you'll see for the Indus River Basin, but it's not yet available on our website. Currently, some of the processing occurs at JPL, followed by processing at the National Snow and Ice Data Center. There is a 2-day lag for the data. Our website shows daily data, but we also write monthly reports describing the current state of the snowpack. The monthly articles are on the first link here, and the daily image updates are on the second link here. This image shows the two maps and graphs we display on our website. On the left is the snow cover fraction map, and the second column is the snow covered area over the Western US in context with data from the last 20 years. The dark black line shows data from this year and is updated through the beginning of March in this image. The dotted black line on top shows the maximum year from the last 20. The light dotted line on the bottom shows the minimum year. The gray area shows the interquartile range with the average or mean in the center. The third column shows snow-covered days. Snow-covered days, as we discussed in the last lecture and question and answer session, are the same as persistence or duration of snow cover for the water year. The final column on the right shows the snow cover days for this year in context for the last 20 years. Similar to column 2 for snow covered area, it shows this year as the dark black line, and here is updated through the beginning of March. The dotted black line on top shows the maximum from the last 20. The dotted light line on the bottom shows the minimum year. The gray areas show the interquartile range with average or mean in the center. Here I'm showing the snow cover fraction map on the left and the snow covered area plot on the right through April 13th. If you go to the website, you'll see these updated till today. And again, here are the snow covered days map on the left and the snow covered days in context with the last 20 years on the right. These are also updated to today on our website. In addition to snow cover and snow cover days, we provide the percentage of median SWE compared to the last 25 years and the change in SWE for the last 24 hours from SNOWTEL, ground operated sites in the Western US. The time lag on this data is much shorter than for the satellite data. This year, there is a strong La Nina pattern with higher than average SWE values in the north and lower than average SWE values in the south. The data I just showed is for the Western United States. We also provide functionality to select major river basins of the West and the Western states through this drop-down menu. You are now familiar with each individual graph that I explained. This is an example from the upper Colorado River Basin. You can see in the center bottom graph that the upper Colorado River Basin fared a bit better midwinter and didn't drop below the minimum satellite record as the Western US did. Here is another example of a major river basin. California is well below average for SWE, as seen on the lower right. On the lower left, we can see snow cover is quickly melting due to the lack of recent storms. Data for this water year can be accessed by going to the daily images and data page and clicking on download data on the upper right. In addition to the automated summaries and data, we've been writing monthly articles that summarize the data across the Western US, states and basins since February of 2020. I'll show some examples from this month's article, but you can view all of this on the website. We'll start with some informative bullets for those who want a quick summary, shown here on this page. We then dive into an overview of the current conditions. These tables show information about the Western basins, the Western US, basins, and states summarized. We write quite a bit and usually include some spatial maps. For example, the difference in snow cover percent on the left here. You can see the March storms in the Front Range of Colorado and Wyoming brought snow cover to above average conditions, as shown in blue. While snow cover fraction can quickly increase or decrease, snow cover days accumulate over the water year. On the right side, you can see that accumulated over the year, snow cover days are well below average relative to the satellite record for most of the Western US. We also summarize snow water equivalent. These figures on the left show the percent of the average SWE from the start of March and from the end of March, both with the La Nina pattern of more snow in the north and less snow in the south. Further analysis on the right in this month's article summarize the monthly change in SWE by state. Interesting events like the polar vortex or a blizzard occurred in parts of the country. On the bottom left, we show a blizzard that occurred along the Front Range in Colorado in March that was on the top 5 record for Denver snow totals. Next year, we hope to adopt some, if not all of these upgrades to snow today, including snow albedo, finer scale subsetting. We've also applied for funding to expand the analysis to all of North America and Greenland using a new spectral mixture analysis model by Ned Bair. Or alternatively, we could process the ModSCAG and ModDRFS data at UC Boulder to improve the lag time and deal like solar zenith issues that we sometimes see in northern states. We'd also like to add other regions like high mountain Asia, as I've shown you in our HiMAT project. The last thing I'll show today are some operational assessments done every 2 weeks by the US Air Force for Afghanistan, Pakistan, and Tajikistan. Briefly, snow cover they use is coarser than what we use at 1 kilometer, and a simpler algorithm than what we use as well. The SWE is from passive microwave algorithms at 25 kilometers applied to a sensor called SSMI. This slide shows the 8 basins in Afghanistan that the assessments are performed over. I'll show a few examples. The assessments are also performed over these 5 basins in Pakistan. Finally, the assessments are performed over these 3 basins in Tajikistan and Kyrgyzstan. So, returning to Afghanistan, I'll show a few examples. Here is the Amu Darya. On the left side is the passive microwave SWE. The blue area shows the historical range since 1987. The red line shows this year's SWE, and the dotted line shows the average. SWE early in the year was higher than ever, but on March 28th of 2021, SWE was near average. On the right side is a binary map. The blue areas show where snow is on that date, while the light green areas show where the snow melted since the last assessment. All of the graphs I'll show now will look the same, except different basins. Here on the left, the red line shows that the Helmand Basin was above average for the beginning of the year, just like the Amu Darya, but not quite as high. Now it has fallen to near the minimum since 1987. The upper Kabul is similar to that. It was above average, but is now below the minimum since 1987. Snow in the Western Helmand has fallen to near zero earlier than usual. In summary, decision trees are a form of machine learning. Ensemble methods perform better than single trees. Random forests randomly select predictors at which to make splits and perform better than typical ensembles. Machine learning can be used for combining satellite data to gain high temporal and high spatial resolution for snow cover and grain size or albedo. Current NASA research in the Hindu Kush Himalaya will produce products to gain an understanding of the source of stream flow. Snow cover and SWE can be used in context of the history to understand this year's conditions. Thank you for your time and watching the lecture. Please bring any questions to the next lab session and we will answer them there.